Hi and welcome back to Podcast School. This is another video podcast in this series of electronic systems, and today we're going to look again at the 555 timer, but this time in astable mode. So what do I mean by astable? I've said there that it allows the output component, whatever that might be, to be continually switched on and off repeatedly at a certain frequency. Okay, so we're going on and off. Last time in this, so this is, okay, let's just label this. This is astable. Last time in the last podcast we saw monostable, where we just, bit wonky, down. So that was monostable. So that was last time, and this time we're talking about astable. Monostable, when we talk about monostable, we mean it has one stable state, and in astable, it means that there are no stable states. And by stable states, I mean states whereby we can say most of the time it's in one state. So in monostable, it's usually off. And it's on for a time, but in astable, it's neither on or off stably. It's on for a time, then off, then on, then off. So there's no stable states. Okay, so that's what we mean by astable. I've just said flashing lights, things that connected to an alarm. You would want that to have an astable output, so that it's continually flashing. You don't want it to stop. So here we are. Here is the basic arrangement for an astable circuit. You notice that we've got the 555 timer as before. We've got a component R1, a component R2 this time, and we've got C as before. And on our outputs, we have our LED connected to our through our resistor. Okay, so again, it's external components that are changing the operation of this circuit. Notice that we have got the pinout diagram here just for reference. So this is what we would expect to see at the output this time. Okay. On and off repeatedly, and of course I want this podcast to end at some point, so we're not going to do this indefinitely, but this pattern would just keep continuing for as long as you wanted it to. Okay. Just one wee point to note here. We've got two times this time. We've got a time called T1 and also a time called T2. T1 is the time where the output is a high, you can see that there, and T2 is the time whereby it is a low, and we can change those. Okay, so sometimes you may want T1 to be very, very large in respect to T2, or perhaps the other way around, but we can change both with this circuit. Okay, so how do we do this then? I've said there that in the astable configuration, and just before, I should have said this earlier, everywhere where there's a red, where I've labelled the text in red, I feel that it's important. So this slide actually has lots of red, so you can see that there's lots of facts in this slide. Anyway, I've said there that in the astable configuration, the trigger input, remember the trigger input is pin number 2. Okay. The trigger input of the IC is connected to the threshold pin. So that's pin 6. You can see that there, look. They're both connected together, pin 2 and pin 6. So the 555 timer is triggered every time the charge on C falls below a third of the supply voltage. So that's the same as in the monostable state. Remember, in the monostable state, we wired up the trigger to a switch, or to the midpoint of a potential divider, where the lower resistor, if you like, was a switch. And when we received a negative pulse, then we actually triggered. Okay, so this time the trigger is directly connected to this part of the circuit here. So the trigger is waiting for the capacitor, the voltage across C to fall to 1/3 of the supply, just as before. Okay, I've said there that therefore C continually charges to 2/3 the supply voltage and discharges to 1/3. Okay, so remember, whenever this circuit is on, or first switched on, the capacitor won't be charged. Therefore, the voltage across C will actually be less than 1/3 of the supply voltage. So in other words, the circuit is immediately triggered. And remember what happens when it's triggered. The threshold does not, or has a high, shows a high input impedance. So the capacitor begins to charge. Okay. Remember also that the threshold voltage, the threshold pin 6, it's almost like a, it's keeping an eye on things. It's a sensing pin as well. And when the voltage on C rises to 2/3 the supply voltage, then the output is set to a high, just as it was in the monostable state. And if you can remember back, at that point, the input resistance flips over, and the capacitor begins to discharge through pin 7, and it will do that through R2 as well this time. Okay, and then of course, as soon as that happens, we're back in a loop, and the voltage will fall to again 1/3 of the supply, and the circuit will once again be triggered, and so on and so forth. So it will happen repeatedly. And I've said there that the 555 timer produces an indefinite series of high output pulses. Just for completeness, I'll just read this out too. It says that there's an additional resistor R2, we've already seen that, compared to the monostable circuit. So the capacitor, and this is important, is charged through R1 and R2. Okay, for the capacitor to get charged, the current must flow through R1 and R2 in series, but is only discharged through R2, because remember, the discharge pin is pin 7. Okay, so there'll be a different time for discharging and charging, and that's important because that allows us to set the mark to space ratio. I don't think I've mentioned that yet, but I'll show you what that is now. Okay, so the duty cycle, or the mark to space ratio, is the ratio of time the output is on divided by the time the output is off. Okay, so in other words, the mark is the time when it's on, the space is the time when it's off. And if you add the mark and the space time together, that in fact is a one cycle, because between those points, between here and here, it's a repetition. We could make the full wave just by repeating this bit. Okay, so the mark is the time when it's on, space is the time when it's off. And I've said also there that for a true square wave, this would be 1. In other words, the space time would be the same as the mark, and we call that a square wave. I've said there, if you look carefully at the diagram above, you will see the timing capacitor, so that's the slide before, capacitor charges through R1 and R2, I've said that already, and discharges through R2 only. Okay, this means that a rectangular wave is produced unless R1 is very small in comparison to R2. In other words, you can ignore R1. Okay. Now, this is the formula for working out what T1 is. T1 is 0.69 times R1 plus R2 times C, and you'll recognize that one. You'll recognize that formula. That's just the time constant for charging a capacitor. Okay. Roughly, we've said 0.69 here. All right. And of course, we're charging through R1 and R2. The discharge time is 0.69 times R2 times C. Okay. So therefore, the total period, the sum of the mark and the space, is t1 plus t2. So that works out to be these two equations added together to give us 0.69 times r1 plus 2r2 times c. And what you should do, I'll not take time to do it here, but what you should do is actually work through the algebra and actually convince yourself that this equation is these two added together. It's just a matter of rearranging the terms and taking out this 1.69 value out to the left hand side. And of course you can almost see it already. Like there's one R2 and there's another one there, so that's where the 2R2 comes from. Okay. Okay, just to finish this podcast then, I've asked you a question here. How fast will this LED flash? So really it's just a matter of plugging in the values into the equation that you were given in the previous slide. I've given you these values. R1 is 1 kilo ohm, R2 is 68 kilo ohms, and C1 is 10 microfarads. And remember, that's 10 to the power of 10 to the minus 6. 10 by 10 to the minus 6, should I say. Okay, so that's our equation, frequency. And remember, all frequency is 1 over the period. So F equals 1 over T. And in the previous slide, you saw that T was 0.69 and then times this bottom line. So in other words, the 0.69, or 1 over 0.69, sorry, equals 1.44. So it's just the reciprocal of 0.69. So that gives you the top line. That tells you where that comes from. And of course, it was T had all this term on the top before, so it's just gone to the bottom. So this is where this equation comes from. So let's plug in our values then. So there you have it. Frequency obviously is 1.44 times R1, and R1 is 1000 kilo ohms. Times 2, 68, R2 is 68,000 kilo ohms, so it's 2 times 68,000, times 0.00001, so that's 4 zeros. Okay, remember it's 10 and it's 10 to the minus 6, so that would be 1 times 10 to the minus 5, and when it's 1 times 10 to the minus 5, you've got 4 zeros after the decimal point. And if you work all that out, you get a frequency of 1.05 hertz, so just slightly more than once a second. So in other words, this LED will flash with these values and the 555 timer, of course, at a frequency of 1.05 hertz, or about once per second. Okay, so that's it for now. Don't forget, as I say every single time, if you haven't got the notes, make sure that you pick those up. You'll not really be able to see this probably online if you're just viewing in your browser. The podcasted version will be of much better quality, so watch that at least, and follow it, say, with the notes. The other thing I just want to remind you of is there is now a Twitter feed for Podcast School, which is always very useful to keep abreast of, because if you sign up to it, which is free, you will not only get your podcasts downloaded to your iTunes, but you will be told the instant one of these podcasts become available by text. So that's quite a good thing. That's it for now then, so until next time, bye bye.